So we're almost there now. We just need to wrap up our argument here. What did we actually just do? We took all the natural numbers, so that's the non-negative integers, 0, 1, 2, 3, 4, and we aligned each of those natural numbers with a function, a mathematical function, inputs to output, so that every natural number had a different function aligned with it. So every natural number, just like when we were mapping between the dogs and the collars, every natural number had a function aligned to it. We then created this new function, f dash of n. And the way that we created it was that we looked up the diagonal, that's defined by f sub n of n. In other words, that defines the diagonal of my table, and we added 1 to it. So that's one of the Cantor functions that I spoke about in the video where I was developing this. And it's a different function from all of the functions which are already associated with a natural number. So in other words, all of the natural number parking spaces, they're already full. They've each got a function aligned with them. And then by looking at those functions, I created a new one which I couldn't fit in. And that must mean that the number of functions from natural numbers to natural numbers is an uncountable infinity, just like the real numbers. And because I already know that the number of computer programs, that's just strings, remember? So those are alignable with the natural numbers. So the number of programs can be aligned with the natural numbers. So that's a countable infinity. The number of functions that I might want to write a computer program for is an uncountable infinity. And that shows you that there are more functions than there are computer programs. So at this point, probably you're saying, well, so what? Okay, so there are some weird potato diagrams where you take in the natural numbers, you output natural numbers, and somehow they're all over the place. They're higgledy-piggledy things. 0 maps onto 5028, 1 maps onto 2, 2 maps onto 6,000,009. How the hell are you going to compute that? And you might think, well, I don't need to worry about things like that. The computer programs that I've written and the functions that I've encountered, I've always been all right. Well, there are problems that you will encounter, real problems for which there is no computer program. And one of the most famous of these is called the halting problem. The idea of the halting problem is that you're going to write a program to predict whether or not another program is going to finish or go into an infinite loop or run forever. So basically, I've got a computer program, P, and I've got a set of inputs to that program, which I'm going to call I, okay? And this is the program under test. I'm going to test this program using my magic halting algorithm, which I'm going to call H. What H does is it takes in the program under test and the inputs to that program under test. So it takes in P and I, and it runs its algorithm and it produces a result. If it produces 1, that means it predicts that the program will halt if you run P with I as input. So in other words, if you run P with I as input, it will halt. It will give you a result and it will halt cleanly. Whereas H of 0 or false, that means that it's going to run forever. Either it runs in an infinite loop or it goes into some kind of doubling thing or something. Basically, it doesn't halt. Now, it'd be really nice if we could actually program H, because I've often, you've probably done this as well, I've often written infinite loops in my programs. I'd like the computer to check for them and say, hey John, you've written an infinite loop. The problem is that the halting problem is non-computable. you can actually prove that no program can exist for it. You can find a proof of that in Gödel-Escher-Bach, I think, and also in the Turing's Vision book. But basically, the halting problem is not computable. There is no way of predicting, in general, whether or not a computer program will halt. And in Turing's Vision, there are lots of other examples of non-computable functions. There's quite a few of them, in fact. So I don't expect you to be able to trot out the proof of the fact that there's an uncountable number of functions. But I do want you to understand that there are different sorts of infinity, and that the computer programs are one sort of infinity and the functions are another sort of infinity. So what I'd like you to do for your tutorial exercises is this. First of all, we know that all sets are finite or infinite, and that all infinite sets are either countable or uncountable. So having heard what I've said, define in your own words what's meant by a finite set, a countable infinite set, and an uncountable infinite set. Give me a definition of those terms based on these few little lectures that I've done. And then what I'd like you to do is think about these 9 sets here, and I'd like you to label them as either finite or infinite. And then what I'd like you to do is to label the infinite sets as either countable or uncountable. So you might like to try and think, can I map them onto the natural numbers? So for example, the set of all theorems of the MIU system, can I map those onto the natural numbers? If you've been listening well to the lectures, I've in fact already given you the answer to that one. So these are the 9 sets that I want you to tell me what size are they. Finite or infinite, and if it's an infinite set, then tell me if it's countable or uncountable. So the first set is the set of all students taking CS103, then the set of all theorems of MIU. So that's all the true strings, and we're talking about the original MIU, the one with the 4 rules. The set of all the prime numbers. You know what prime numbers are. Then we've got the set of n, such that n is a member of the natural numbers as n is less than 5. We've got the set of all the real numbers. The set of all dogs which have 4-letter names, and you can assume that those 4 letters are taken from a finite alphabet. Then we've got the set of all possible subsets of the natural numbers. So a subset is, for example, the one possible subset is just the positive odd numbers, 1, 3, 5, 7, 9. That's a possible subset of n. Think of all of the possible subsets of n. How many do you think there are? That's probably the toughest one. You might know. You might need to look that one up. Then we've got the set of all computer programs. How big is that set? And we've got the set of all functions, which map from a member of the natural numbers to a member of the natural numbers. How big is that set? So that winds it up for the argument about non-computable functions. And for the rest of the class, we're going to be looking at recursion. And recursion is one of the ways of creating infinite things using finite resources.